half hour to go. Pretty much right on topic, right on track here. Acids, bases, and buffers. This is basically, there's a really brief mention of this in your textbook, but electrolytes, I'm sure you've heard of those before because, people talk about Gatorade having electrolytes and stuff like that. But basically, electrolytes, from a chemistry standpoint, they're substances that break into ions in a solution. So if this wasn't, cocoa powder in here, which I will not drink, it's much better in milk. If we were to put something in water and it were to break apart and it broke apart into ions, that would be an electrolyte. So the stuff in things like Gatorade, they put substances in there. Water is your solvent, and it breaks apart. Break apart into these ions so that it can give you those electrolytes like Pedialyte, things like that. So depending on the type of ion that it breaks into, it can also kind of create something that's very acidic or something that's very basic. So acids are those that they are a substance that is going to release hydrogen ions in water. So this down here, this H plus, is a hydrogen ion. And it essentially is a hydrogen atom without its electron. So all we've got here is we've got a proton and we've got an electron, and a proton and a neutron, but no electron. Okay? And the chlorine has got the electron. So if a substance really easily gives off a lot of hydrogen ions in water, it's a strong acid. So some of the common examples of acids that we have in our everyday life are things like orange juice or coffee. So if you drink something or eat something that has a kind of a sour taste to it, it's more acidic than something that is base. And so bases are those that, when they disintegrate, they disintegrate into these hydroxide atoms here. So this OH negative, that is a hydroxide atom. So this is sodium hydroxide. So obviously you get sodium, and then you get hydroxide in water. And it's going to be a base. So some common examples of these are egg whites, milk of magnesia, things that taste bitter, are things that are bases in there. So if you can imagine, if we had get out my whiteboard here, we had our HCl that dissociates into H plus and C chlorine, and we have our sodium hydroxide. Gonna go into sodium plus. So if you can imagine, if we had these two different substances and here the hydroxide the hydroxide would accept this hydrogen atom. So it's looking for a hydroxide atom. They're looking for each other. And they combine, so you take H plus OH negative, and you combine together, and you essentially are going to get good old-fashioned water. And you do that. Okay? And then could the sodium and the chloride combine? Oh, sure. You can combine those two together, and you're gonna get salt. You're gonna get plain old table salt and combine those two together. So just kind of keep it in your head. What you need to know is that acids have those hydrogen, those those hydrogen ions in them, and bases have hydroxide atoms. So if you look here, here is a pH scale. And did you guys ever do an experiment in high school where you had to take pieces of litmus paper and then touch it onto different substances and see what color it would change into? Do you remember that vaguely back in high school? It was 30 years ago for me. Okay, so I can remember. Hopefully you guys can too. So now I just told you how old I am, which is okay. So, depending, so these are different things. So gastric juice, this is what's in our stomach that's going to digest our food, is a kind of on a stronger side of acid. We have apple juice. Black coffee, just plain good old-fashioned black coffee, has a pH of 5. Let's see here, just to kind of see if I can freak you guys out any at all. But Coca-Cola is 2.52. It's a very strong. You know how you can take a can of Coke, put it in a glass of water, drop a rusty nail into it, and it'll dissolve the rust off of it. And we drink that stuff, and it's so good too. Red Bull is 3.37, so it's also a strong acid. And anything that's below like 6 will start stripping the enamel from your teeth. So, anyways, I just thought that would be kind of fun to maybe freak you guys out a little bit. Like, okay, no more soda or Red Bull for you guys. But hey, I know we are who we are. Okay, so here's our pH scale here. And we can have something called a neutralization reaction, which is what I was just describing on my whiteboard here, is that you take sodium hydrochloric acid and sodium hydroxide, you combine the two together, you're going to neutralize them out. And so you're going to get salt and water. So hydrochloric acid is kind of right down. It's a pretty strong acid. Sodium hydroxide is a pretty strong base as well. Put them together, you neutralize them out. This is the basis, kind of, for antacid tablets. Because, your stomach's sour and you got heartburn. What you're doing is you're swallowing a base to try and neutralize the pH in your stomach. It's kind of the basis for, antacids. But sometimes we don't want the pH to be changed. Sometimes you want it to stay like it is. And so when we have that situation, we might have that strong acid or that strong base. We'll have it in a buffer solution. So here is sodium, I can't remember that, sodium hydroxyl something. Let me look it up in a textbook real quick. I remembered it, but then this whole thing with the trying to get that, they just call it a sodium, they're just calling it a buffer salt, sodium bicarbonate. Sodium bicarbonate is what they're calling it. This is your buffer. So when you add more acid to it, it's going to combine with the buffer so that the hydrochloric acid will still kind of stay strong. So it's going to combine. So we have this right here, which is H2Cl3, which doesn't tell me what it is. It's going to combine to, this is a weak acid, and this is a salt. So basically what's going to happen here is that the acidity is not going to change. It's not going to get much stronger. It's not going to get much weaker. And the same thing that they kind of show you with the bases here is that you end up with, here's a strong base. You end up with kind of a buffer and water. So basically what I want you to take away from this, I don't want you to try to memorize any of these formulas because they're not what they need to be. I know I'm not explaining it very well. So one is example of when a buffer is used. Let's see. I'm trying to think of an example of a buffer. Why do you want to keep acidity distinct? Well, let's take a look at your stomach, for instance. I could probably answer the second question better than I can answer the first. Is that, if let's say we ingest something that is a base. Most of our food is either neutral or acidic, but let's say we ingest something that is a base. We don't want the acidity of the stomach, and if we ingest something with a lot of acid into it, like those people who, I don't know why, but they decided they want to take the ghost pepper challenge, and they eat all of these ghost peppers until, have you ever seen those YouTube videos of that? Don't try this at home. They get these peppers and they eat them, and oh my gosh, it's just and they try not to drink water or milk or bread or anything like that, but if you swallow something that's very acidic, we don't want the gastric juice in our stomach to really change. So even though our stomach is very acidic, it has buffers in there to prevent it from changing, because we know what works for us and what digests food. If we throw a strong acid in there, and then all of a sudden we're changing the pH of our stomach, that essentially is going to allow the gastric juices to start eating away at the linings of our stomach, and we're going to get an ulcer. That's one reason, aspirin is harmful to some people. Some people, when you add in aspirin to their stomachs, it can result in ulcers and gastric bleeding, because it's changing the chemical composition of the stomach. Again, you throw a huge base in there, let's say I were to drink some milk, which I do every morning. I don't all of a sudden want, my stomach acid to go up to somewhere between 6.6 and 2.0 to 4.2 or whatever, because nothing else I eat is going to digest correctly. So that's an example, and I hope that helps you, kind of understand why we want to keep them the same. So in terms of our bodily functions, we want to keep our stomach acid right where it needs to be, so we can digest the food and not the lining of our stomach. Okay, that makes sense? I hope that helps. So hit me up in the chat box and let me know if I answered your question good enough for you. So like I was saying, I don't want you to memorize formulas. I want you to memorize, what an acid is, the definition of an acid, definition of a base, and what buffers do. I don't need you to memorize any of those formulas that are in your textbook. We don't need to go that deep. We just need to have a basic understanding of that. So, all right, then there are some organic compounds, and some of these we're going to run into again and again. So one of them is carbohydrates. We always talk about carbs as being a bad thing. They seem to be like the evil villain of dieting over the last several years. I don't know. I live on carbs, and I don't know what my problem is. I can eat an entire large pizza in a sitting, and this is what happens. So don't know. But everybody's different in their makeup, but they're a very important energy source. They got a lot of sugars in them. They got a lot of, they got a lot of complex sugars and starch and things like that. So knowing just the basics to know for carbohydrates is that they're an energy source, that they are carbon, hydrogen, and oxygen, which it kind of says in a name, carbohydrate, carbon, C-A-R-B, hydrogen, H-Y-D, oxygen, O, carbohydrates. Kind of tells you all it needs you need to know in the name. Just remember that an energy source that they are basically they're composed of a lot of sugars and starches. And so you have your monosaccharides, disaccharides, and polysaccharides. So a saccharide means sugar. So mono is like one, di is two, poly is many. So we're talking about a simple sugar like glucose, disaccharides, sucrose, polysaccharides, just starches. So it's just more of a matter of how complex is that sugar. We're also going to talk about proteins, especially when we talk about DNA and muscles and amino acids and things like that. So for lunch, if you're going to have this giant 3-hour session with me, which I commend you guys for staying alert and engaged throughout the whole thing. It's really hard to kind of do this for 3 hours, and trust me, we're coming up on a nice big break, so we'll get there. You want to eat a high protein lunch. You eat carbs, you're going to want to fall asleep. Think of your Thanksgiving meal. Even if you take the turkey out of it, potatoes, carbs, stuffing, carbs, pumpkin pie, carbs, bread, carbs. No wonder you want to sleep for 10 years after you get done eating Thanksgiving meal. But proteins are an energy source, and they don't quite put you to sleep as much as carbs do. And so proteins are from amino acids. So remember your carbohydrates, carbon, hydrogen, oxygen. Proteins, amino acids. Okay. They're also used as a structural material. They're used for so many things. They're structural materials. They're used in enzymes. They can be used in hormones. They're used to form hemoglobin, which carries oxygen around. There's just so many things that they can be used for. And then the last thing is your lipids, and your lipids are just basically your fats. So they also contain carbon, hydrogen, and oxygen, but usually the oxygen is much lower ratio. So carbohydrates tend to have a ratio. So let's see. Carbohydrates tend to have a ratio of that. So give or take. Some exceptions here. So if you have C6H12O6, you've got glucose. And then it's not, so it just tends to have that pattern. Whereas lipids, I know they have CNH, I think it's 2N, but the O is different. So the oxygen, there's much fewer oxygen and lipids than there are in carbs. So there's kind of similar if you want to look at it from an atomic standpoint, but just not having that oxygen there makes them have very different properties. So they don't dissolve in water, so but they will dissolve in alcohol. So you can always bring that up next time you're at the club or whatever. You're like, hey, did you know that alcohol will dissolve fat? And be careful, don't get slugged. I don't know, but they will. So if you have an alcohol, lipids will dissolve in an alcohol. They are the building blocks. The triglycerides. We've heard about triglycerides as being kind of a bad thing. We don't want to get them too high of a concentration in our bloods. And then we have saturated fats, and we have unsaturated fats. So saturated fats are those that have single bonds. So these are like it kind of saturated with hydrogen atoms. Like this, sort of saturated completely with hydrogen atoms all the way around it. So that's a saturated fat. But if you get an unsaturated fat, what you get is something like this. And so on and so forth. So, making sure I got that right. There you go. You get something like this. So instead of having just a single bond between, if you have something that looks like an equal sign, that's a double bond between this. There's a double bond here, and there's a double bond here. So you're not quite surrounded by all these hydrogen atoms like you were if you had a saturated fat. So, this is I'm a Detroit Lions fan from Michigan, Michael Stafford. So this is poor Stafford on any given day. When we have the lineup here, he's not quite saturated by his back end defense sometimes. Poor guy. Okay. All right, and we also have a subcategory of phospholipids, which we'll talk about when we get into cell membranes. And then, lipids get such a bad rap, but they're so important to the body. They're important to cell membranes, they're important to steroids. Cholesterol is a good thing. We need cholesterol in our bodies to have our bodies work correctly. But, we don't want to have too much of a good thing. So we're starting to find out now that we may be a little bit wrong about our thinking on cholesterol. So maybe in 20 years from now, we'll be like, wait, never mind. Cholesterol doesn't have anything to do with heart problems. You never know. We learn and evolve. A couple others organic compounds that I mentioned are the nucleic acids. These are, again, proteins. So you get nucleic acids that are kind of chains. So DNA is a big one, and we'll talk about that a little bit in chapter 3. And specifically mentioned adenosine triphosphate. And this is a compound that's used by the body. It's how we store energy. So when we make ATP, we store energy in those bonds. And then when we need energy, we break apart the ATP to get our energy. So, okay, are there questions on that?